Hey guys, welcome to the first presentation on acids. It's called Drop the Base. It says anger is an acid that can do more harm to the vessel in which it is stored than to anything on which it is poured. Mark Twain. So here's what we already know. This is what you should know from early in the year, that acids are solutions with hydronium ions in solution. Now by hydronium ions, what we mean is H3O plus, which is sometimes referred to as H plus as well. So disassociated protons or hydronium ions. This is the one that's actually called hydronium ions, but a lot of times you'll see it written as this is H plus and then an aqueous there as well. Those are actually mean the exact same thing. So because of that, we can say either one. Bases are solutions with a hydroxide in solution, and we have hydroxide as OH minus. Now, acids and bases can be classified as strong if they ionize completely. This is something we talked about earlier in the year, the idea of complete disassociation. What complete disassociation means is that, for example, if you have HCl, there really is no HCl. Instead, what happens is it becomes H plus and Cl minus. In fact, this part of the arrow isn't really there because it disassociates completely. Okay. And we also know that acids and bases are classified as weak if they do not ionize completely. So if you had something like, say, acetic acid, it does go back and forth. It reaches an equilibrium. So because of that, this would be classified as a weak acid. Okay, so let's see if we can get this to... All right, so it says an arrhenius acid. You should already know what an arrhenius acid is, that it is a substance that increases the concentration of H plus or H3O plus, depending on how you want to look at it, when mixed with water. Okay, you should also know that Bronsted-Lowry means that it donates a proton. So, for example, you have something like, I don't know, HCl, and then you have water. And what it does is it actually donates its proton to water. And then finally, you have the Lewis definition of an acid, which is where a substance can accept electrons. So these are all from earlier in the year when we talked about the very definition of acids and bases, and you should be familiar with them. You should also be familiar with common acids. You see things like acetic acid in vinegar. You see things like carbonic acid that's in your blood. You see things like citrus acid in fruit juice and hydrochloric acid in your stomach. Phosphoric acid tends to be in your in things like cokes. And sulfuric acid you don't really see a lot in common usage because it's a pretty strong acid. So as far as what's a base, the Arrhenius definition of a base is the one where you have an increase in the hydroxide ions that are present. Whenever you have the Bronsted-Lowry definition of a base, what that means is it's something that accepts a proton. So you could have something like HCl plus water, and what happens is the water actually acts as the base because it can take this proton on and become H3O plus. So because of that, it's said to be a Bronsted-Lowry base, water is. And that a Lewis base is anything that can donate electrons. So the common bases that you see is you see acetone, you see that in fingernail polish remover. Ammonia tends to be in a lot of cleaners. Calcium hydroxide tends to be, I believe it's in, well, no, that's magnesium hydroxide is in milk of magnesia. Pyridine is a base that's in DNA, I believe. And then sodium hydroxide is the most common base that we'll be looking at. So it says all fingers are thumbs, or all thumbs are fingers, but not all fingers are thumbs. All Arrhenius acids are Bronsted-Lowry, and all Bronsted-Lowry are Lewis. So when you look at it, Lewis incorporates the most of everything. A slightly more narrow definition is Bronsted-Lowry, and a slightly more narrow definition is Arrhenius. This is where we're going to operate the most of the time. We're going to be talking about Arrhenius acids and Arrhenius bases. You do need to know the difference between the different definitions of the base, but this is where we're going to operate. Okay, so here's an example. It says draw a mechanism showing how HCl meets the definition of each type of acid. If this question seems familiar, it's because it is. You should have done something like this before, earlier in the year. You have H plus and Cl minus. You have, that's the definition of an Arrhenius acid. We have to add water. Okay, here's the definition of Bronsted-Lowry. You have water, and what happens is this thing disassociates. It comes here to the oxygen and kicks those electrons onto chlorine. So what you're left with is you have chlorine minus with its 8 electrons, and then you have H3O, and then you have a plus. Okay, and then finally you have the definition of the Lewis definition was where we have to look at electrons. So you have something that is accepting the electrons. You have H2O, and you have lone pairs of electrons here. And when you look at it this way, you see HCl. These electrons can come over here to the hydrogen. So the hydrogen is accepting those electrons and it's kicking these electrons onto chlorine. So we still have the octet rule satisfied for all these things. Except this time you have this, which is H3O plus you have Cl minus. Octet rule satisfied for all of them, but you do have a plus and a minus. So you do need to memorize the strong acids and bases. These are things that you have to know without question. There's one that's missing here. It should be H3PO4, which is phosphoric acid. So you see basically all of the halogens, except for hydrofluoric acid. The reason for that is the attraction between hydrogen and fluorine is so great that it's not considered to be a strong acid. It doesn't disassociate. Other than that, you see the halogens, and then you also see the rest of the eights. So you see sulfate, nitrate, perchlorate, phosphate, and actually chlorate is there as well. A lot of times it's left off, but chlorate should be there as well. And then for here you see the strong bases, which mainly consist of group 1 and then group 2 cations and hydroxide. Whenever you name acids, you should be familiar with this. It's similar to polyatomic ions, but there's a big change. Anytime you see an 8, like sulfate, instead of saying 8, if that's the ion, so for example, if you have H2SO4, instead of saying sulfate, which is the anion there, we take off the 8 and we replace it with ic. So it becomes sulfuric acid. Okay. If you have something that has an ite, it becomes us. So for example, this right here is nitrite. So what we would do is we'd say nitrite. We cancel out the ite and we replace it with us, and we get nitrous acid. Okay, and finally, when you have an element by itself that ends in I, like you have here with HBr, okay, this is an element by itself. It ends in ide, so it becomes hydro, and then ic. We don't put the dash there usually, ever. Okay, so you have hydro, and then bromic acid. So those are the common rules for naming. You should be familiar with those from first year chemistry and also from earlier this year. The rules for naming bases are really easy. It's the same as you would do for any sort of polyatomic ion. You would just name this right here, which is the cation. You would name it sodium. And then most of the bases we're going to work with are hydroxide, so sodium hydroxide. Okay, remember that if you're doing this, if you're working with a base, anytime you have something that is a transition metal, so something like FeOH3, you have to be sure and specify the oxidative state. Because hydroxide has a charge of -1 and there are 3 of them, that means that the iron has to have a charge of +3. So we would call it iron 3 hydroxide, where remember that Roman numeral represents the positive charge. Okay, conjugate acids and conjugate bases. What you see here are conjugate acid-base pairs. So HCl is the acid, which makes Cl minus the conjugate base. So anytime you get rid of an H, its conjugate base is whatever it is whenever it's minus that H. So for example, if we start off with something like H3PO4, which you see here, if you get rid of an H, whatever's left becomes the conjugate base. Now if I were to start with this, if I were to start with H2PO4 and say what's its conjugate base, the conjugate base would lose an acid or lose an H, you'd have HPO4. Okay, so you can have a conjugate base right here for multiple things. If I were to ask what's the conjugate acid, you add an H. If you were to say what's the conjugate base, you subtract an H. Now if you look, you see water right here. Water is the conjugate base to hydronium, and it is the conjugate acid to hydroxide. So that's really what we're looking at right here, is the relationship between hydroxide and hydronium and water. That's really what we're interested in. Now, one of the things that you should notice is that whenever you have a really strong acid, the conjugate base is very, very, very weak. In fact, it gets to the point where it's considered to be negligible. So the stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. So whenever you have something that's a weak acid, like this is a very weak acid, it is a stronger base. Now water is kind of the ultimate. It's not an acid or a base, so it's considered to be negligible, which means it ends up being a really strong base. Okay, so if you look at this, we measure acid strength and pH, and we talked about this earlier in the year. pH is the negative log of the hydronium concentration or the hydrogen concentration. It's a logarithmic scale, which means that in order to go from 1 to 2, you have to increase by a factor of 10. Actually, it's the opposite. When you go from 1 to 2, you actually decrease by a factor of 10. But you have to change by a factor of 10 to change the scale number 1. Okay, POH is the same way, except it's the negative log of the hydroxide concentration instead of the negative log of the hydrogen concentration. Basically, anytime you see a P in front of something, it means take the negative log of. You will see later pKa. All that means is take the negative log of Ka. Now, the pH scale is based on a 0 to 14. This is actually based on the disassociation of water. It doesn't really have anything to do with any sort of maximum or minimum. You can have pHs that are negative. You can have pHs that are plus 15 or higher. So you can go on either scale, but these tend to be what most pHs and pOHs stay within. You see an example, battery acid tends to be somewhere around 1. Something called lye, which is sometimes used to make soap, is somewhere around 14. So you have really strong acids and really strong bases. Now, one thing that you will notice is that distilled water is right in the middle, which means that it has a pH of 7. Now, one of the things that you always do is whenever you're working with a strong acid, something here between 0 and 1, you always want to have baking soda there to eliminate it. Because baking soda is slightly basic, it's way better to have a slightly basic thing on your skin than it is to have something that's a strong acid. Likewise, when you're working with something with like lye, it really makes sense for you to have something right around here, something like vinegar, to help neutralize a strong base. Because although we tend to think of acid burns and things like that, a base can do just as much damage to you as an acid. Okay, now when we're looking at measuring the acid strength, there's a couple of different ways to do it. One is a pH probe, the second is litmus paper, and there's actually a third one that's actually called a titration. And the titration we'll get into in a little bit more in the next presentation. But really, basically, what these things do is they're ways of measuring the hydrogen concentration. Now, there are advantages and disadvantages to each of these. The litmus paper is really easy and it's quick. Okay, it's really quick and easy. But the problem is there's no exact specification of what it is. Really, what you're going to do is you're going to look at the pH paper and you're going to say, hey, it's somewhere between 1 and 2. And that's great. It's really good because it kind of narrows it down, but at the same time, it doesn't give you the specificity that you want a lot of the times. The pH probes that most labs in high school are associated with will be able to give you a pH reading of something like 3.42, which is a lot more accurate than you would get with something like litmus paper. So because of that, the pH probe is the preferred method. Now the problem is it's way more complicated to use a pH probe. The first thing that you have to do is you actually have to standardize it. In order to standardize it, you have to put the pH probe in something that you know the pH of. Now they do actually sell these. They're called pH standardization solutions. And you would actually take this pH probe, you'd put it in a solution, say the pH is 4. And then you would put it in a second one, a different solution, say the pH is 1. And with those two things, now it can calibrate it. And once you calibrate it, it's good to go. The problem is you actually have to calibrate it every time you use it to make sure that it's reading the way that it's supposed to. In addition to that, you have to store these things in a solution because if it ever dries out, it doesn't work. So although it's really great as far as its accuracy is concerned, it's nowhere near as easy as something like litmus paper. Okay, so now the pH scale is based on the disassociation of water. Just like we've talked about in terms of equilibrium, water can randomly disassociate into a hydronium and a hydroxide. Now, if you look at this, this is not really a balanced chemical equation. Instead, you'd have to put like a 2 right there. Instead, it tends to be written like this. You tend to see H2O goes to H plus plus OH minus. So you don't tend to see it in the form with a 2, but this is the form we tend to see it in. Now, this is a random occurrence. It does happen. It just doesn't happen very much in water. Now, if you were to have it happen in some sort of more acidic solution, it could definitely happen. Now, since we have some sort of equilibrium expression right here, you can write any sort of K value you want. Remember, any K value is just simply the products, which we have H plus and OH minus, over the reactants, which is H2O. Now remember, H2O is a liquid, so it's left out of this equilibrium expression altogether. So if you were to look at this, you can actually measure what this disassociation of water is. But what you can say is for every H, there's going to be an OH. And so what you can say is, okay, well, that's going to be x and that's going to be x. The kW value is actually 1 times 10 to the minus 14th. Okay, so when you have this 1 times 10 to the minus 14th number, when you solve for x, you end up getting 7, or 1 times 10 to the negative 7th for each number. Well, that means that you have equal amounts of hydronium and hydroxide. When you take the p of this value, like pKw, you end up getting 7 for each of these. Or if you look at it for the whole thing, it ends up being 14. This 14 right here is really just another way of saying pH plus POH equals pKw. Okay, so pH plus POH ends up equaling pKw. And so that's what you have here. And where that comes from, you have the hydroxide concentration times the hydronium concentration, and then that equals the Kw value. Well, that's the expression we had on the previous page. Well, if you take the P of each of these, remember when you multiply two logs together, it's the same thing as adding those two logs. So this is where that expression actually comes from. And this is where you can relate pH to POH. So for example, if you're given an acidic compound, you can actually figure out what the POH is going to be as well. And that's what we see here. Now this is actually a more complicated question than it looks like originally. We'll talk about why it's a little bit more complicated than it looks, but for now let's treat it as a basic question. So it says number 1, what is the name? So let's write out what it is. I've got 2 H's, I've got an S, and I've got, looks like 4 O's. So that would make this sulfate. Since it's sulfate, it becomes sulfuric acid. So that's the first thing. We've named it. Now that we've named it, the next thing it says is what is the pH and POH of a 15.8 molar solution? Well, the first thing we need to do is we need to look at this. Whenever you have the disassociation of sulfuric acid, it's what's called a polyprotic acid because there are more than one proton. So in actuality, you're going to have something that looks like this. It's going to go to HSO4 plus H, and then there's going to be HSO4 is going to go to H and SO4. Now, if you ever go beyond general chemistry, you may actually explore this relationship in terms of this K1 and this K2, and the overall K of the reaction is K1. Whoops. The overall is going to be K1 times K2 ends up being the K for the acid overall. Okay, for now, we're not going to look at that. We're going to treat this as just a polyprotic acid. In other words, we're going to treat it like both protons disassociate. In reality, they don't, but the math gets extremely complicated when you don't. So for now, we're going to treat it in a simplistic view of saying H2SO4 goes to 2H and then SO4. Okay, when we do that, now we can say, all right, those are my reactants. My initial concentration that I have is 15.8, 0, and 0. Now, I know that H2SO4 is a strong acid, which means that it disassociates completely. So the change is I'm going to lose all of this and end up at 0. That's the definition of a strong acid, is I'm going to end up at 0. Now that makes this, remember this is on the other side, is going to be plus. But instead of being plus 15.8, I'm going to treat it like it's plus 31.6. And this is going to be plus 15.8. Now, I do have the sulfate concentration, but when we're talking about acid and bases, nobody really cares about that. What we care about is this number right here. That number represents the hydronium concentration. Now, hydronium concentration right here is telling me that H plus actually has a concentration of 31.6 molarity, which is a little bit ridiculous. It's really, really, really high. So if you were to find the pH would be the negative log of 31.6. Now when you do the negative log of 31.6 in your calculator, the first thing that you're going to realize is you end up getting a negative number. And so remember we talked about earlier, we said that the pH scale you can actually have negative numbers on, and that you shouldn't be concerned with that because the 0 to 14 thing is kind of a general guideline. So the second thing that you should realize is that you end up getting not only quite a negative number, which ends up being, let's go ahead and put it in real quick, 31.6. It ends up being negative 1.5. Okay? Well, based on the fact of this, we can figure out what the POH is. And remember, the relationship based on water is pH plus pOH has to equal 14. So when you plug this in, you have a pH of negative 1.5. That plus pOH has to equal 14. That ends up giving you a pOH of 15.5, which is, remember, also outside that traditional scale. So when you have extremely concentrated acids and bases, they actually fall outside the traditional range. But this right here, remember, is a simplistic view of things. What really happens is when you have a polyprotic strong acid, that first proton comes off 100%. But that second proton is actually subject to what we call the weak acid rules, which we will talk about a little bit later, but not in a polyprotic situation. So now the next one, it says write an equation for the ionization of water. So we'd say water ionizes. It becomes H plus OH minus. And then it says what is the pH and pOH of water. Remember, this is based on the disassociation of water. So we can say Kw is equal to 1 times 10 to the minus 14th. That's one of the constants that we have. That equals H plus and then OH minus. So we have X and X. You can actually solve. X ends up being 1 times 10 to the minus 7th. Once you do that, remember, X refers to both the hydronium and the hydroxide concentration. So because of that, you can take the negative log of it, and you get 7 for the pH, and you get 7 for the pOH. They end up being the exact same values. Next it says A has a pH of 3.6. How many hydronium ions are present in a 25 ml sample of solution? So the first thing we're given is the pH, which is 3.6. We're given a volume of the sample of 25, excuse me, not 2.5, but 25 milliliters. And we want to know the number of hydronium ions. So we want to relate this thing back to number. So the first thing I do is I'm going to work with the pH. Remember, pH is equal to the negative log of the hydronium concentration. So the first thing that I want to do is say, okay, I have pH. 3.6 is equal to the negative log of H plus. So whenever you're doing this, you're trying to solve for H, you've got to get rid of this log. So what you do is you do what's called an anti-log function, which is also known as an exponential. Whenever you have a log, this represents a log base 10. So since it's a log base 10, you can take 10 and raise it to the negative 3.6. The reason why you do 10 to the negative 3.6 is you're trying to cancel out this negative as well. So on the other side, you have 10 to the log of H plus. When you do this, it's actually called an anti-log because that cancels out. And what you're left with is 10 to the negative 3.6 is equal to the hydronium concentration. When you do that in your calculator, you get something like 2.5. So your H plus ends up being 2.5 times 10 to the minus 4th. Now what that means is that right there is your concentration in molarity. So now if I want to know how many hydronium ions are present in the sample, the next thing that I have to do is I have to go back to stoichiometry. So remember, 2.5 times 10 to the minus 4th molarity really means 2.5 times 10 to the 4th moles per 1 liter. So the first thing that I would do is I'd say, okay, 1 liter is 1,000 mils. Okay, and then I can say 25 mils. But even that would only give me moles, and I want to know actually how many hydronium ions there are. So reaching way back, you have to say 1 mole is equal to 6.022 times 10 to the 23rd. That's terrible handwriting. 10 to the 23rd. So if you want to know how many hydronium ions there are, even at this pH, it'd be 2.5 times 10 to the minus 4th divided by 1,000 times 25 times 6.022 times 10 to the 23rd. As a result, you end up getting something like 3.76 times 10 to the 18th. And those are hydronium ions. Now that's a lot of hydronium ions, especially considering it's only a 25 ml sample and the pH is pretty reasonable. So you have to remember the reason why this number is so big is because you're talking about the number of ions, and atoms and ions are extremely small. Next it says what is the pH of a solution containing 1.4 times 10 to the minus 10th molar hydronium ions. It says classify the substance as an acid, neutral, or a base. So the first thing you do is you say, okay, I have the concentration, the concentration is 1.4 times 10 to the minus 10th. So what I want to do is I want to find the pH. The pH is equal to the negative log of the hydrogen concentration, or the negative log of 1.4 times 10 to the minus 10th. One thing you should realize is that the concentration of hydronium is very small because of that 10 to the minus 10th. So when you put this in your calculator, you would say log of 1.4 10 to the minus 10th. And when you put this in your calculator, you're going to be getting a value of about 9.85. Well, that's significant because remember, anything with a pH that is greater than 7 is considered to be a base. So even though you were given the concentration of hydronium ions, that doesn't necessarily mean it's an acid. In fact, anything that's greater than 1 times 10 to the minus 7th molarity, if the hydrogen concentration is greater than that, then it's an acid. So anything times 10 to the minus 6, times 10 to the minus 7th, times 10 to the minus 4th, times 10 to the minus 2nd, those are all things that are going to be acids. Anything that has a hydronium less than 1 times 10 to the minus 7th ends up being a base. The last thing we need to talk about in this presentation is the weak acids and weak bases and the disassociation that results from those. So the first thing that you'll notice right off the bat is when we talk about weak acids and weak bases, you should be familiar with the definitions already as being something that disassociates very similar to ions. Now remember, when we talked about ions before, we talked about things that disassociated completely, or, as in the case of some solutions, they disassociated partly. So we had to kind of specify whether something would disassociate completely or partially, like we had, for example, sodium chloride. When you put it in water, always went to sodium and then chlorine because it dissolved 100%. But if you compared that to something like silver dichromate, it didn't disassociate nearly as much, so we had to use Wright's charts to go ahead and figure out how much disassociated. It is very similar when we talk about weak acids and weak bases. When we talk about weak acids and weak bases, they come to an equilibrium. So what you see right here is that it disassociates into H plus and A minus. Well, that's partially true, but remember, it comes to an equilibrium. So you should actually have lines like that indicating equilibrium. Anytime you have an equilibrium, you can write a disassociation expression, also known as an equilibrium constant, where you have Ka equals H plus A minus over HA. Anytime you see this, you should be thinking Rice chart. So, strong acids. Now, we don't deal with Kas for strong acids, and the reason why is the expression becomes meaningless. Basically, the Ka expression is trying to say, okay, well, when do we come to equilibrium? Well, if you have something that disassociates 100%, well, you would do the equilibrium expression just like you've done. This value is essentially 0. The problem with that is when you divide something by 0, it becomes undefined. It's mathematically ridiculous to do that. And so because of that, we don't deal with Kas for strong acids and bases. It's just not something that we do. Now, a strong acid for the purpose of this class is anything that disassociates 90% or more. So if you have a strong acid, something like 2 molar HCl, that means that the hydronium concentration is also 2 molar. Now, if you have something like H3PO4, for now, we're going to treat it like it would be, so it's 1 molar H3PO4, that would be 3 molar H. Now, it's not always going to be the case, but we're going to treat it like that for now. So the initial concentration of the strong acid equals the final concentration of H plus, okay, but you also have to take into account polyproducts, so don't forget that. Whenever you have weak acids will partially disassociate. The expression is crucial to determining H plus because remember, something is in equilibrium. When it's in equilibrium, we can actually solve for it using the equilibrium expression. So you can no longer say that the initial concentration is equal to the final concentration. That doesn't work anymore. It only works for strong acids. So an example of this, it says the acid dissociation constant for acetic acid is 1.58 times 10 to the minus 5th. What is the pH of the solution of 0.15 molar acetic acid? So the first thing we want to do is we want to write an equation for it. So we have acetic acid, which is CH3COO, it's acetate, and then they usually put the H at the end, disassociates into H plus and CH3COO minus the acetate ion. Those are my reactants. The initial concentration that I have is 0.15. I originally have 0 and 0. The change that I have is actually end up going to be, I don't know yet, minus x plus x plus x. As a result, my equilibrium expression ends up being 0.15 minus x, and x. So now I can go to an equilibrium expression because now I know what something is in equilibrium. To kind of simplify it, I'm going to say Ka is equal to HA over HA. Okay, because I don't want to write out the whole acetic acid. Okay, so as a result, I can now plug in the values. So I'm going to kind of clear out just a little bit of room here. And we're going to say H, or 1.5, 8 times 10 to the minus 5th, is equal to x squared. We erase the second x, but you have x here, and then there's another x for the a. So because of that, you have x squared over 0.15 minus x. This is where it becomes really handy for you to know the shortcut. If this ends up being less than minus 2, it is not going to appear in significant figures. So because of that, we can actually take this x away. And I know that doesn't sit well with a lot of you because it doesn't work mathematically, but you take that away because it's less than minus 2. You don't have to deal with the quadratic equation at this point. So then you would just multiply across. You'd say 1.58 times 10 to the minus 5th times 0.15, and you end up getting 2.37 times 10 to the minus 6th equals x squared. You take the square root of both sides, and when you do that, you end up getting something like 0.0015, we'll call it 4. Okay, that equals x. Now remember, x, you can go back to your original expression, is going to represent the acetate or the hydronium concentration. It's the same thing because they're both solved for x. As a result of that, if I'm trying to find the pH, pH is equal to the negative log of that x value. So when I do the negative log of 0.00154, I'm going to get a pH, which should be somewhere around 2. Let's check it real quick. Log of should be something like 2.81. Now pHs are generally reported to 1 to 2 significant figures. Now the significant figures calculations are somewhat complicated whenever you're looking at it in terms of logs and exponentials. Okay, so we'll spend a little bit of time on that in class. Next, the base disassociation. Base disassociation is just the same as acids, except you're dealing with OH concentration instead of H+. So when you're doing this, it's easier for you to find the POH than it is for you to find the pH. So once again, whenever you have a strong base, because it disassociates completely, this is a meaningless expression. So the initial concentration of strong base is equal to the final concentration of OH minus. Once again, be careful for things that are polyhydroxyl. So something like this is a dihydroxyl. So you just be aware of that. A weak base partially disassociates, just like we talked about. You've got your BOH on the bottom, you've got your OH on the top, and this statement is no longer true. So the process for weak acids and weak bases is the exact same. Now finally it says to calculate the disassociation constant for pyridine is 1.8 times 10 to the minus 9th. It says what is the pH of the solution? That's 0.15 molar pyridine. So the first thing you want to realize is this right here is actually the Ka value. So the first thing that we need to do is we actually need to solve for the Kb value. Whenever you solve for the Kb value, how do I know that? It's just something that I remember when I looked up. So whenever you do these, there's an expression that's actually very helpful. So remember we had the idea of, well, Ka times Kw has to equal, or excuse me, Ka times Kb has to equal Kw. So because of that, if I know the fact that my pyridine constant is 1.8 times 10 to the minus 9th for Ka, that times KB has to equal 1 times 10 to the minus 14th. So because of that, I can solve for my KB value pretty easily. It's just 1 times 10 to the minus 14th divided by 1.8 times 10 to the minus 9th. It ends up being KB is 5.56 times 10 to the minus 6th. So now at this point, we can take that KB value and we can go ahead and solve our expressions. Now instead of writing out this entire structure for pyridine, which I don't really want to do, okay, let me go ahead and write the KB value. 5.56 times 10 to the minus 6th. Instead of writing out the whole thing for pyridine, I'm just going to write it as BOH. It's way easier that way. I don't have to write out the whole expression for what pyridine is, and I can say this. Now remember, those are my reactants. So my initial concentration that I have is 0.15. Some of you may be asking yourself, why didn't I just use that? Well, the problem with that is that's the proton disassociation. It's not going to match this equation for a base. The initial concentrations are 0 and 0. The change I don't know. And then my equilibrium expression is this. Now if you look, this is the exact same thing that we had in the previous example, except this time it's a base. So when I look at this, I would say KB is equal to BOH over BOH, or in our case, it's 5.56 times 10 to the minus 6th equals x squared over 0.15 minus x. Remember, that's smaller than a negative 2, so we can cancel this x out, and then we would solve. Now when we do this, we end up getting a value of x equaling 9.13 times 10 to the minus 4th. Now remember, x represents the OH concentration. Okay, so in order to find the pH, first I'm going to find the POH. POH is equal to the negative log of OH, which in our case is 9.13 times 10 to the minus 14th. So now we take the negative log of that, and we end up getting 3.04. So the POH is equal to 3.04. The final step is you're trying to solve for pH. Remember, pH plus POH have to equal 14. So 14 minus the 3.04 ends up giving you a number of pH is equal to 10.96. Okay, so there's another thing that's called percent ionization. And percent ionization is the concentration of ionized substance divided by the original concentration. So this comes into play when we talk about something being a strong acid. Whenever something is a strong acid, that means it's 90% or greater is the percent ionization. So if we were to look at this previous example, you have your amount that is actually ionized. And my ionized value is this 9.13 times 10 to the minus 4th. So I can say 9.13 times 10 to the minus 4th is my initial concentration that is ionized. Now divide that by my original concentration, which was 0.15, multiply by 100, and that tells you your percent ionization. Now one thing that you'll notice is for weak bases and weak acids, the percent ionization number ends up being very, very small. And in this case, it is 0.61%, which is very, very, very small. Finally, it says calculate the percent ionization of a solution of 0.01 molar benzoic acid where Ka is 6.31 times 10 to the minus 5th. Benzoic acid, you should know, is going to be benzate, okay, and then with an H. So it's going to have that benzene structure right there. Okay, that's beside the point. So now if we were to look at the percent ionization for the solution, you have HA goes to H and A. You can write this even if you don't know the structure of benzoic acid. Those are my reactants. Next I do my initial, 0.01, 0, 0. My change, I don't know what it is. It's going to be X plus X and plus X. And then you're going to have 0.01 minus X, X, and X. As a result, you can say that Ka is equal to H times A over HA, or in our case, it's going to be 6.31 times 10 to the minus fifth is equal to x squared over 0.01 minus x. Because that's a small number, I can cancel out that x, and you end up getting something like 6.31 times 10 to the minus seventh equals x squared. So you plug that into your calculator, you'd say 6.31 times 10 to the minus seventh, take the square root of it, and when you do that, you end up getting something like x is equal to 7.94 times 10 to the negative fourth. Okay, remember that x value represents the concentration of H, or how much is disassociated. So because of that, if I'm trying to find my percent ionization, I would say 7.94 times 10 to the minus fourth divided by my original concentration, which is 0.01, times 100. 0.01 times 100 actually cancel out. So then what I can say is that my percent ionization ends up being 7.94 times 10 to the minus fourth percent. Now that is very rare that it actually happens. It just happened because I have 0.01 molar. Don't think that these are always going to cancel out. It just did in this one particular case.